Question number 1 says, imagine a place in the cosmos far from all gravitational and frictional influences, so you're way out in outer space. Suppose that you visit that place and throw a rock. Yes, Kate?
Is that actually a picture of a spaceman throwing a rock?
Yes, that's actual Hubble telescope footage. You're right, I did. It's far enough away from anything that it's minimal.
So we're not going to take that.
No. There's no forces at all. Good question. Okay, so the question is you throw a rock, will the rock gradually stop, or will the rock continue in motion in the same direction at a constant speed? Question number 3.
Macintosh.
Oh, really? Macintosh?
Yeah, that's what I said.
He is so funny.
Question number 3. Mac and Tosh are arguing in the cafeteria. Mac says that if he flings the jello with a greater speed, it will have a greater inertia. Tosh argues that inertia does not depend upon speed, but rather upon mass. Who do you agree with, and explain why?
What kind of jello?
It's rainbow. Question number 4. Supposing you were in space in a weightless environment, would it require a force to set an object in motion? If I take my coffee cup and go out into outer space, do I still need a force to get it in motion?
Yep.
There's no gravity, there's no friction. Do I need a force to get it moving? Fred, Gage.
Let's go.
Fred spends most Sunday afternoons at rest on the sofa watching pro football games and consuming large quantities of food. What effect, if any, does this practice have upon his inertia? Does it increase his inertia? Does it decrease his inertia because he's at rest? Or does it have no effect at all on his inertia? Ben, too close. He's being chased through the woods by a bull moose, which he was attempting to photograph. The enormous mass of the bull moose is extremely intimidating, but if Ben makes a zigzag pattern through the woods, he will be able to use the large mass of the moose to his own advantage. Explain this in terms of inertia and Newton's first law of motion. No, Gage. No. The moose, so this is the explanation. The moose has more mass, so he has less inertia, so he's not able to make zigzags as easily. The moose has more mass, so he has more inertia, so he's not able to make zigzags as easy. Or it will not work, the moose is still able to make the zigzag pattern, and Ben is going to get run over. Which one do you agree with? Question number 7. Bo.
We're doing a very good diagram.
Bo. 2 bricks are resting on the edge of a lap table. Shirley, she's short, stands on her toes and spots the 2 bricks. She acquires an intense desire to know which of the 2 bricks are most massive. Since Shirley is vertically challenged, she is unable to reach high enough and lift the brick. She can, however, reach high enough to give the bricks a push. Discuss how the process of pushing the bricks will allow Shirley to determine which of the 2 bricks is most massive. What difference will Shirley observe, and how can this observation lead to the necessary conclusion? So, is it A, the brick that moves more has more inertia and is heavier? The one that moves more has more inertia and is heavier? The brick that moves more has less inertia and therefore is lighter? Or both bricks will feel the same and move the same distance, even though one is more massive than the other? Number 8. Okay.
Oh, look at that fat cat.
My old friend Luke out below drops an approximately 5 kilogram fat cat. weight of 50 newtons off the roof of his house into the swimming pool below. Now, before I go on with this is fiction. This cat was not actually thrown off a roof.
Was it actually 5 kg?
And even if he were, it would be a stunt cat of some kind.
5 kg.
No cats were harmed in the making of this question.
Yeah, because I probably would.
Okay, so we've got a 50 Newton cat He's being tossed off the roof of a house into a swimming pool. Upon encountering the pool, the cat encounters a 50 Newton upward resistant force that is assumed to be constant. So in other words, gravity is pulling down on the cat with 50 newtons, and the water has a buoyant force of 50 newtons up. Use the description to answer this following questions. Which one of the velocity time graphs best describes the motion of the cat? Is it graph A, B, or C? These are velocity time graphs. Which one of the following dot diagrams, remember when we did the ticker tape stuff, right? Which one of the following dot diagrams best describes the motion of the falling cat from the time that they are dropped to the time that they hit the bottom of the pool? The arrows on the diagram represent the point at which the cat hits the water. So, is it A, is it B, or is it C? The red arrow indicates when the cat hits the water.
Which never happened, right?
No, he hit the water. Now, while this cat was being launched off the roof, several of Luke's friends were watching the motion of the falling cat. Being physics types, like yourselves, they began discussing the motion and made the following comments. And I believe there are 10, 11, 12, and 13. There's 4 of them.
Did one of them actually help the cat at least?
Yes. Don't worry, there was no cat's harm. The cat's good. He'll live another day. He's got 8 more lives. Indicate whether each of the comments are correct or incorrect and support your answer. So, once the cat hits the water, the forces are balanced and the cat will stop.
Well, stop basically be like cement, so it would die.
Question 11. Upon hitting the water, the cat will accelerate upwards because the water applies an upward force. Remember, this is not your average everyday cat. This cat weighs exactly 50 newtons, and the water exerts an exact upward force of 50 newtons.
It's a superhero.
Question 12. Upon hitting the water, the cat will bounce upwards due to the upwards force. Again, I caution you, this is not an everyday average cat. This is a cat that weighs exactly 50 newtons, and there is exactly 50 newtons upwards. Last question. This one is the most important one of the day. If the forces acting upon an object are balanced, then the object A must not be moving, B must be moving with a constant velocity, C must not be accelerating, or D, none of these.
I'm none.
All right, let's look at some answers. Gage.
What do you want me to do?
Press enter.
They're supposed to put an answer for me. Oh, okay.
Oh!
Whoa!
Well, what do you know? Everyone got that one right.
That's good.
Yes. The object will continue in motion.
50%.
Okay, obviously everyone got number 1 right. So even though I'm way away from gravity and way away from friction, right, I will continue in motion at the same direction at a constant speed. That's Newton's law, right? Now, question number 2 is practically the same question. The correct answer is 0. Is that what this one is? They might get 0?
No.
Why is it 0?
We never mentioned that because there's no mention that there's any sort of force.
You're right. Neither of these is a force, and neither of them is an acceleration.
They're just going.
A 2 kilogram object is the mass.
You never mentioned there's still like no friction or anything here.
It says how much net force. The key is how much net force is required. You just told me one question ago that an object in motion will stay in motion, and then you turn around and you say that you need a force. An object in motion will stay in motion. Now the difference here is that this is in space and there's no other forces. The difference was here is that you all assumed, even though it doesn't say that, you all assumed that it was on Earth. And even if you did assume it was on Earth and that there was a friction force, it says net force. In other words, if friction is -5, then you need 5 newtons and giving you a net force of 0. A net force of 0 to keep it moving. It is a trick question. It's the same question that I told you I was going to ask over and over again yesterday. It's exactly the same question, Tristan. It's exactly the same question as, is this 50 newtons and 50 newtons, is it moving? Okay? It's the same concept. I'm going to ask it to you again later. Maybe. I won't tell you. Macintosh, who's right? Ooh, better not write on there with a pen. Tosh. Inertia does not depend upon speed, it is mass. What depends upon speed is called momentum, and that's a little different. Okay? Inertia is simply the tendency of the object to stay at rest. Bigger things are harder to get going, harder to stop too. Suppose you're in a weightless environment, would it require a force to set an object in motion? Absolutely it would. Right? Because if you've got F equals ma, if you're going to set an object in motion, then you need a acceleration, and it doesn't matter whether any other forces, a force is required for an acceleration. If you need to change an object's speed or velocity, you need a force. There's a force, gravitational force. My friend Fred, what does sitting on the couch consuming chips and cheesies and whatnot do? It increases your inertia.
But he's just sitting there.
Yeah, well, he's eating food and getting fat.
Yeah, but you said it depends on his inertia at the moment.
Yeah,
If
but
he's not in motion, then it shouldn't affect his inertia.
no, things not in motion can have inertia. Like my filing cabinet has a lot because it's very big.
You use your filing cabinet for examples a lot?
Yes, it's right here.
Really?
Okay,
Oh, that's right.
stand too close.
Uh-huh.
So what about this moose?
B.
It is B. The moose has more mass, so he has more inertia, so he's not able to make zigzags as easy. A classic example of this is the Titanic. They saw the iceberg, they were turning, they just are really massive, so they have a lot of inertia, so they can't come up with enough force to make that acceleration quickly. Okay? Big things have a lot of inertia. It doesn't depend on how fast they go. The 2 bricks. Which one is correct? I believe it's B. The brick that moves more has less inertia and therefore is lighter. If you've got 2 things that are the same size and you give them both a push, right? Obviously the one that moves farther has less inertia, is therefore lighter. Look out below. Correct answer? B. There's a lot of B's in here. Who said I told you? Tony? Why? Tell us, explain why it's B, Tony.
Well, that was my guess.
Oh, you guessed?
Because it's accelerating and its velocity is going in a negative direction and it stops.
Okay. Well, it doesn't stop. It stops what? Stops accelerating, right? When the cat is falling, he's accelerating. He's got 50 newtons of force. So his velocity, this is the part you guys need to listen to. His velocity is increasing negatively. But when he gets to the water, Gage, 50 newtons, 50 newtons, what's the net force? 0. And when you have a net force of 0, Gage, you have an acceleration of 0, which means your velocity does not change. Your velocity does not change.
Cat does not sink.
No, the cat does sink at a constant speed. He's increasing. Here, let's just say, let me put some values here. He's falling at -1, -2, -3, -4, and then he continues falling at -4. He's reached like terminal velocity. Now, many of you will argue, well, when this cat jumps in the pool, right, he's going to actually slow down, right? I said over and over and over again, Gage,
This isn't your
This
typical-
is not a typical cat. This is a cat that weighs exactly 50 newtons and a pool that exerts exactly 50 newtons on it.
Is that point four?
It says right here, use this description. So be careful.
Have you raised $13?
That's how much I have, yes. I would like some more. All right, which one of these dot diagrams best represents the cat?
Hold it.
It's going to be A.
Because it doesn't.
A. Okay? Here, the dots are getting farther apart. It's accelerating.
Then sinks at a
When you
constant
get to
speed.
the water, you sink at a constant speed. Exactly.
You wouldn't be
Chris.
going the same speed that you were falling.
You were talking when I explained it earlier.
In your teeth, guys.
Okay? Again, this is not a typical cat in a typical pool. This is a special cat that has a weight of exactly 50 newtons and a pool that has a special upward force of exactly 50 newtons, which means that the net force is
There's yours.
0, which means the acceleration is 0, which means you are staying at the same speed.
That's not gonna happen.
Again, this is not a special cat, or this is not a regular cat. I think I've said it a few times. Okay, so once the cat hits the water, the forces are balanced and the cat will stop. That, of course, is
False.
false. Is any part of that statement true? I heard some people talk about it. I heard someone say, but the forces are balanced. That's true. But if the forces are balanced, again, what does that mean?
Constant.
It means the acceleration is 0 and the velocity remains constant. It does not mean that the cat will stop. That would be a change in velocity.
So say the cat was 50 meters and the water was like 60, would that mean he'd go back up? Or
Yes, he would.
He bounced.
He would bounce.
Poor kitty.
He would
My
bounce.
kitty will splat.
Good question.
He used a rock.
Upon, what's fun with the picture of a rock be?
If that cat's a fucking
Upon hitting the water,
I'll use the polar bear.
okay. Upon hitting the water, the cat will accelerate upwards because the water applies an upward force. Again, part of that is true. There is an upward force, but again, the forces are balanced, giving us an acceleration of
0.
0.
Yeah, process that if there's a net force. Yeah.
Yes, there is definitely a point to all this game.
No, I'm just asking what.
Yeah. Upon hitting the water, the cat will bounce upwards due to the upward force.
False.
No, because the forces are balanced, giving us an acceleration of.
0.
Are you getting the point here?
Yeah.
Let's see if you got it. Let's
I
see
didn't
what you
get
did
it.
on 13. Do you want to change your answer?
Yes. But I can't.
If you had to change your answer, what would you change it to?
C.
Exactly.
right.
Okay. The object must not be moving. What's the counter? Give me like 2 more minutes. 2 more minutes. If the force is acting upon an object balance, then the object must not be moving. Not true, because it could be moving at constant velocity. It must be moving with a constant velocity. Not true, because it could be stopped. Must not be accelerating? Absolutely. Balanced forces means a net force of 0, which means an acceleration of 0, which means constant velocity, but that is either 0 or whatever number that is, right? So the answer is C. This, my friends, this statement right here is the point of today's lesson.
Understood.
Okay? I will be testing this in some fashion. I won't just come out and ask it like this. I will be testing it some way.